coming back to our natural hazard risk assessment framework, we present now a theoretical model of requirements to assess all the process chains leading from natural hazard process to the processes involved in determining the consequences of a natural hazard process. That means the impacts, the responses, the damages, and the economic evaluation of these damages. So in this picture, we can see that the chain of processes that has to be modeled via numerical models, via conceptual models, via empirical models, entails 5 steps, 5 distinct modeling steps. The first modeling step, labeled by A, is the process modeling, followed by the second modeling step, which is the impact modeling, that is quantifying the impacts in terms of loading configurations on the objects exposed to the flow, on the elements at risk, if you want. The third phase is the response modeling phase. That means modeling the behavior of the structures exposed to the hazard process, bending and other kind of responses. That means in principle performing a structural mechanics analysis. Once we know how the elements at risk behave under the loading scenarios, we can perform a damage accounting, that is assessing damages starting from critical states of the structures, failure states of the structures. Once we have assessed the damages in terms of physical alterations of the structures, we can start performing an economic valuation. That means attach economic values to the damages. In principle, evaluate the monetary value of the reinstatement of the damaged structures. These modeling steps are logically quite integrated, and on a detailed look, we might also argue that certain results also backpropagate to the previous step. Imagine that, for example, a residential building is collapsing under the load of a certain hazard process. Obviously, this change in state affects also the process itself, and depending on this, the impact on other objects. But this is a level of sophistication that is, let's say, beyond the scope of our course. But I have to say that in this relation, research efforts have been made to set up an integrated modeling that takes into account the unfolding of the hazard process, the impact on certain structures, the responses of the structures within the same modeling framework. So it's possible to couple the effects of the single modeling steps and to see also this backpropagating effects, or if you want, these couplings that occur. Normally, however, in natural hazard risk assessment, we prefer keeping the steps separated, and the result of the modeling step A, that means the process modeling, is in general represented in forms of maps of flow velocities, flow depths, pressures, erosion and gradation if the employed model is fit for representing morphological changes throughout the simulation. These results depend on a series of modeling steps in the catchment. That means, first of all, the representation of the catchment hydrology based on the catchment hydrology in selected computational domains, normally where the elements at risk are located. We perform hydrodynamic modeling, either in a 1D, 2D, or 3D fashion. And this hydrodynamic modeling may also take into account sediment transport processes. Once we have the representation of the flow velocities, the flow depths, and the pressures in both in space and time, so we have several maps that represent the variability of these parameters in the computational domains and also throughout the event time, if you want. We can start calculating the impact on the exposed structures in terms of static and dynamic loadings, geotechnical actions. Just imagine that channel incision might destabilize from a geotechnical perspective a building, even without interacting with the building directly, because the geotechnical mechanisms could be due to a loss of bearing capacity of the soil, for example. Also, building physics might be thought of. Just imagine the wetting of the building envelope in a so-called static flooding that may last for several days or even weeks. In this case, the wetting of the building envelope might entail a deterioration of the building structure and of the building materials in the long run, and so also building physics comes into play. Generally, the impacts are accounted for by quantifying forces, pressures on the building envelope, on the construction, and so on, changes in profiles in terms of geotechnical actions, failures, slope failures, and so on, that account for these geotechnical failure mechanisms. Wetted surfaces and also the exposure time might play a relevant role. And last but not least, also the intrusion pathways. Just imagine to compare two different geometries of the buildings. In one case, you have the doors, the windows exposed to the approaching flood. In the other case, you have the same openings, let's say, on the protected side. Obviously, this differences also in the geometrical configuration of the building might affect the overall response of the building. If solid material is intruded into the building and the building is not designed for resisting to the vertical loads of this solid material that resides within the building, the floors might collapse due to these additional loads, for example, and therefore also the intrusion pathways may play a relevant role. In many cases, the intrusion pathways play the most relevant role. Just imagine that people might be, let's say, caught, if you want, within a building due to solid material intrusion, and this might be the cause of also fatalities I experienced it in an event documentation in South Tyrol in 2012, where in principle certain buildings exposed to debris flow resisted from a mechanical perspective to the impact, but due to inconvenient opening locations, solid material easily intruded into the building, and due to this phenomena, several fatalities had to be registered. So in principle, if we have the impacts, we can calculate the responses through suitable response models. Obviously, we have to choose the, let's say, the right model for the complexity of the structure. It's in simple cases we might employ critical frame models where the structure is let's say represented as a frame structure. In more complex cases we might employ finite element models to simulate the structural response. Also for soil mechanics, now finite element models are available that enable a quite detailed modeling of the mechanical behavior of the soil. In relation to the building physics, there are a lot of models also available that allows us to retrace, if you want, the moisture dynamics throughout the wall, and also other mass transfer processes. The response normally is accounted for through the quantification of stresses, strains in the structure. If we only determine one maximum value of the stresses and strains, we might compare these maximum values with the maximum permissible values, and obviously depending on this comparison we might conclude that the structure is going to fail under determined loading conditions, or is going to resist to the specified loading conditions. In case of hill slopes, we apply safety factors for slope stability. That means that if the stabilizing factors divided to the stabilizing factors are inconvenient with respect to the chosen safety factor, we conclude that the slope is going to fail. Otherwise, we conclude that the slope is going to remain stable. With respect to soil mechanics, again, we might calculate the bearing capacity of the soil, and with respect to building physics, we might judge the responses to wetting if we know the time of exposure of the building envelope to the flow process. Detailed 3D models are also available that allow us to calculate water intrusion into through the building envelope, and therefore to judge what might happen within the building. For solid material, I have to say that modeling approaches currently available are still, if you want, deliver an approximation of certain intrusion processes, a rough approximation, and therefore let's say that these intrusion processes are studied, or let's say are represented well for liquid water discharges, but not so well or not so precisely for solid material transport processes. In principle, the overall result of the application of the response modeling in form of the application of